This is a black hole. Black holes are probably the most famous objects in physics, and the reason is simple. They constantly push our understanding of nature to its limits. They challenge gravity, quantum mechanics, thermodynamics, and even the way we think about information. We usually describe a black hole with one famous sentence: nothing can escape a black hole, not even light. And in a classical sense, this is true. Once something crosses the event horizon, it cannot come back. But quantum physics adds a surprising twist. A black hole is not completely black. It can emit radiation. And over an unimaginably long time, it can even lose energy and slowly evaporate. This phenomenon is known as Hawking radiation. Today, we are going to understand why black holes can radiate, what this radiation really means, and why it is one of the deepest connections between gravity, quantum physics, and thermodynamics. Before we can understand Hawking radiation, there are two ideas we need to clarify. The first one is the event horizon. A black hole is not simply an object with a very strong gravitational pull. A more precise way to describe it is this: a black hole is a region of space-time where beyond a certain boundary called the event horizon, all possible future paths lead inward. This sentence may sound strange, but it contains the central idea. The event horizon is not a solid surface. It is a boundary in space-time. If something crosses it, it is no longer simply difficult to escape. It becomes physically impossible. Not because the object is not powerful enough, but because beyond that boundary, there is no future-directed path that leads back outside. Even light cannot escape, and light is the fastest thing in the universe. This is why we usually say that nothing can escape a black hole. In the simplest case, for a black hole that does not rotate and has no electric charge, the size of the event horizon is determined by the Schwarzschild radius. Rs equals 2mgc squared. Here, m is the mass of the black hole, g is the gravitational constant, and c is the speed of light. If your distance from the center of the black hole becomes smaller than this radius, you have crossed the event horizon. From that point on, returning to the outside universe is no longer physically possible. The curvature of space-time is so extreme that every possible future path points deeper inside the black hole. The second idea we need is the quantum vacuum. In classical physics, vacuum simply means empty space. No matter, no particles, nothing inside. But in quantum field theory, the vacuum is not truly nothing. Modern physics describes particles as excitations of underlying quantum fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. And these fields are present everywhere, even in what we call empty space. So the quantum vacuum is not the absence of fields. It is the lowest energy state of those fields. And because the fields are quantum objects, they can still fluctuate. This is why in quantum physics, empty space is not completely empty. The vacuum still contains quantum fields, and those fields can have fluctuations. This idea will be essential because Hawking radiation does not come from ordinary matter escaping from inside the black hole. It comes from the way quantum fields behave near the event horizon. Now, we can finally look at the phenomenon itself. Hawking radiation is a very complex effect, so it is often explained using a simple picture. This picture is not exactly what happens, but it captures the main idea. Imagine we are very close to the event horizon of a black hole, but still outside it. In the quantum vacuum, fields can fluctuate. A common way to visualize this is to imagine pairs of quantum excitations appearing near the horizon. You can think of them as a particle and an antiparticle. Normally, these pairs do not become permanent observable particles. They quickly recombine, and no lasting radiation is produced. But near the event horizon, something different can happen. If one part of the pair crosses the horizon while the other remains outside, the two can no longer recombine. The outside part can move away from the black hole and be observed as radiation. This outgoing radiation carries positive energy, but energy cannot appear from nothing. So in this simplified picture, the partner that falls into the black hole carries negative energy relative to a distant observer. The total energy is conserved, but the energy of the black hole decreases, and because mass and energy are equivalent, the black hole slowly loses mass. This is the intuitive picture behind Hawking radiation. But we have to be careful. This picture is only a metaphor. Hawking radiation is not literally made of particles escaping from inside the black hole. Nothing escapes from inside the event horizon. The real explanation is deeper. In quantum field theory, particles are excitations of fields, and the vacuum is not the absence of fields. It is the lowest energy state of those fields. But near a black hole, the presence of the event horizon changes how quantum fields behave. The horizon separates the field into two regions, one that can be observed from the outside and one that remains hidden beyond the horizon. A distant observer cannot access the full quantum field behind the horizon. Because of this, what would normally be described as vacuum does not appear completely empty anymore. For the outside observer, it appears as a thermal state, and this thermal state is what we call Hawking radiation. This radiation is named after the physicist Stephen Hawking, who theoretically predicted its existence. By studying quantum fields near the event horizon, Hawking found a surprising result. A black hole is not completely black. To a distant observer, it behaves as if it emits radiation with a thermal spectrum, and this means something extremely important. If a black hole emits thermal radiation, then it must have a temperature. The full equation for this temperature is not very simple, but the key idea is its dependence on the mass of the black hole. The Hawking temperature is inversely proportional to the mass. TH is proportional to 1/m. This means that the larger the black hole, the colder it is. And the smaller the black hole becomes, the hotter it gets. But if Hawking radiation carries energy away, that energy must come from somewhere. It comes from the black hole itself. And because mass and energy are equivalent, as Einstein showed with E = mc², losing energy means losing mass. So, according to the theory, a black hole that emits Hawking radiation slowly loses mass. And as it loses mass, its temperature increases. As its temperature increases, it emits even more radiation. This creates an evaporation process that becomes more intense as the black hole becomes smaller. However, for astrophysical black holes, this process is incredibly slow. The time required for a stellar mass black hole to evaporate is vastly longer than the current age of the universe. This idea opens the door to an even deeper question. What happens to information? In quantum physics, information is encoded in the quantum state of a system. It represents everything that, in principle, would be needed to describe the physical state of what fell into the black hole. When an object crosses the event horizon, that information becomes inaccessible to an outside observer. But if the black hole emits radiation, it loses mass. And if after an enormous amount of time the black hole evaporates completely, we are left with a fundamental question. Where did the information go? Was it destroyed? Was it hidden? Or was it somehow encoded in extremely subtle correlations inside Hawking radiation? This is known as the black hole information paradox, and it is one of the reasons Hawking radiation is so important. And with this, we have reached the end. We have followed the story almost all the way into a black hole. We have seen what happens near the event horizon, why nothing escapes from inside it, and how, outside the horizon, quantum fields can make a black hole appear to radiate. Hawking radiation shows us that black holes are not just cosmic traps. They have temperature, and slowly they can lose mass. A black hole is not completely black. It is where gravity, quantum physics, and thermodynamics meet. If you enjoyed this video, consider subscribing to the channel and leaving a like. Thank you for watching, and I'll see you in the next video.